Hello everyone. Thanks for coming. I'm Real Kajiwara. I go by Sylph01 on the internet, and today I will be talking about adding security to Microcontroller Ruby. You get it, the title. Okay, yeah. So slides are available through this QR code or the URL. I'm going to tweet this and also get this up on Discord. I recommend you to open the slides and follow along because I have a lot of text. And don't worry, I'm not that kind of security guy that traps you into like loading bad stuff by scanning this QR code. Let me get this on Discord, then start. Yep, I think it's on Discord now. So. Hello. I do a lot of stuff. If anything on this slide catches your interest, let's talk later. And I do a lot of stuff that is more relevant to this talk. I am a freelance web developer focused on digital identity and security. And I've been worked on writing, editing, and implementing standards in the W3C and the IETF. So previously at RubyConf Taiwan, I gave a talk titled The Adventures in the Dungeons of OpenSSL, where I implemented a HPKE or hybrid public key encryption using the OpenSSL gem and also by extending the C extension of OpenSSL gem. So after gaining some experience with C extensions and cryptography libraries, I came up with a question, why not implement cryptography into microcontrollers? Or can we have TLS in PicoRuby? So our target environment today is PicoRuby plus R2P2, which is done by Hasumi-san. PicoRuby is a Ruby implementation that works on microcontrollers, and R2P2 is a shell system that works on it. And the most well-known use case is the PRK firmware, where you can run Ruby on keyboards. And this is a Raspberry Pi Pico W, which is a board that runs the RP2040 microcontroller, which is a dual-core ARM Cortex M0 Plus at 133 megahertz. And it has 264 kilobytes of SRAM, not megabytes, and also 2 megabytes of flash, not gigabytes. It is very small, and the small size of the SRAM will become important later. It also has wireless LAN with a CYW4349 chip, and it costs 1,353 yen as of April, and which is around less than $10 at the current rate. And also, this is Giteki certified, so we can legally use wireless in Japan. And MicroPython is already able to connect to the Wi-Fi, connect to the internet, and do HTTP, HTTPS. And this is how MicroPython connects to the Wi-Fi access point. So we wanted something similar to this, so I started the project ASMR, or project adding security to microcontroller Ruby. Actually, it's more like adding SSL TLS to microcontroller Ruby, or more accurately, it's adding networking to microcontroller Ruby, but this doesn't have any mean value, so I changed the title to this. So I have a demonstration, but Wi-Fi is very iffy to do on real time, so I have a video. So this is a R2P2 shell system. We can start up IRB. We initialize the Wi-Fi driver, and then enable station mode that connects to the access point. Then it returns true, so we're going to use the connect blocking function to connect to the access point with the SSID and the password. This is the actual password. I'm not showing my actual home SSID and password. So, and then after it's connected, we're going to instantiate the HTTPS client and connect to example.com/. Oh no, it's not working. So we're going to retry again. Then it's succeeded in getting the content. So yep, I will explain about the failure later. So let's go back to the slides. So here's the obligatory warning when talking about security. Cryptographic API is very prone to misuse. If you're going to use it in production, please consult an expert before going into production. And also, gems that entered PicoRuby and R2P2 master branch already, they are pretty much prod ready. But everything else that is especially the thing that touches networking hardware, should be considered experimental. There are some stuff that needs to be done before merging. And also, I am treating PicoW as a normal computer whenever I can. And this is not trivial at all. Embedded bugs are very hard, and there could be many things that I've been missing. I am able to treat the PicoW as a normal computer thanks to Pico SDK and R2P2. So first, let's talk about cryptography in PicoRuby. Quick recap, this is how you do SHA-256 in Ruby. You require OpenSSL gem, you get the instance of digest, then call updates multiple times, then call hex digest, or call the hex digest method of the SHA-256 module, then do the whole thing. And this is how you do symmetric key encryption, AES in Ruby. To encrypt, you instantiate the AES128 object, then call encrypt, then set the key in and initialization vector, then call update on the text you want to encrypt. Then to get the final block, you call cipher.final. And to decrypt it, you do pretty much the same thing, but you could call the cipher.decrypt first. And why did we not implement OpenSSL into PicoRuby? It's because it's too big. OpenSSL does everything, so the binary becomes too big to go into embedded systems. So there are cryptographic libraries specifically built for them, such as embedTLS and wolfSSL. And Pico SDK uses embedTLS, so we decided to go with that. And embedTLS has build options to only include necessary cryptographic functions, and you can see what is included through the r2p2/include/embedtls.config.h. And then when developing cryptography, you want to be able to see the encrypted content, which is a binary string. So we use base 16 or base 64 to see through the binary. But PicoRuby didn't have them. Why? Because it's for base 16 and base 64 are for humans, not for machines. We don't have enough space for human friendliness in the embedded world, so we didn't even have them. So I added this first so that debugging crypto is easier. The base 16 and 64 MRB gem is a simple example if you want to go into MRB gem development. And this is how AES is done in PicoRuby plus embedTLS. It looks pretty much the same as OpenSSL, and this is what SHA-256 looks like. It's pretty much the same. So PicoRuby already had CMAC using embedTLS before I went in, and I added the most commonly used algorithms, AES for symmetric key encryptions. I added two modes, one for the non-AE80 mode, which is CBC, and one mode for the AE80, which is GCM. Then I added the most commonly used function, which is SHA-256, which is known to be secure today. I did not include SHA-1 or MD5 because it is known to be insecure, so you don't have to use them. So let's go into the implementation details, or I'll introduce you to how to make MRubyC extensions. So when writing a C library wrapper, you want to wrap this library's context value, which is a value in C, into a Ruby object, so that we can keep track of the context through an instance value. So in C Ruby, it is done by using the rtype_data macro. In MRubyC, it is done a little bit differently by creating an instance with the MRBC instance new function, which takes a VM, the pointer to the class, then it takes the size of the buffer to create. So here we want to wrap the context struct created by OpenSSL in embedTLS. And to define methods, you might have seen CRuby's RB-define method, which takes a class name function pointer, which has the number of arguments specified in the RB-define method function. And you can get arguments from the function's arguments, but in MRBC, it is also done a little bit differently with the MRBC define method, which takes a pointer to the VM, the class, and it takes a string name and the function pointer. So we don't have the number of arguments, so we take the arguments using the getArgPosition macro. So using this knowledge, this is what the initialization of the digest instance looks like. So first, we are getting the algorithm ID of a SHA-256 with getArg1. So it is specified in the first argument. Then we are going to instantiate the digest objects with a buffer size of the embedTLS MD context T. Then we're going to take the pointer to that buffer, then call the embed TLS MD init to create the context into that buffer. Then we will call some more embed TLS functions to set up the buffer properly, then to return the instance value itself. Next, we're going to show how the update function looks like. We will first take the wrapped context out of the instance, this embed TLS MD context T star CTX, that part, and then pass that CTX into the embed TLS functions. When you define an instance method, you want to call the MRBC incref, which is the second to last line, to prevent the object from being deallocated. Without this, if you call the instance.update after this function the next time, the object will be deallocated at that time, so it will result in a segfault, and you don't want that. Note that we only implemented APIs with updates and finishes, the multiple call APIs, instead of the APIs that encrypts the whole buffer at the same time, which is called a one-shot API. In a memory-constrained environment like PicoRuby, it is better to have multiple call APIs instead of one-shot APIs, because to use the one-shot API, you need to have the first, you need to have the whole buffer of the string. You need to have a buffer that has the same length, which means that you need to have twice the memory of the original string. With multiple call APIs, we can process partially encrypted strings, send them, then free the buffer to continue with the rest. And when doing cryptography, using fixed nonces or random values, initialization vectors are a bad idea. It reduces security significantly. For example, the PlayStation 3's code signing key leaked because of a reused ECDSA nonce. So to do cryptography securely, we need a random number generator. But do we have a random number generator like we have in the computer, like dev-random? No, we don't have them. So we need to build a random number generator from what we have in Pico. And we use the ring oscillator to extract random bits. And you can use this with the RNG gem that is in PicoRuby. The ring oscillator is a chain of NOT gates that flips with the clock. So it flips 0, 1, 0, 1 according to the clock. So depending on the timing you to access the ROSC, you will randomly get a 0 or a 1. This is the code to get the random byte, a random 32-bit 32-bit integer. It gets an 8-bit integer, sorry. Here we are getting the random bit from the hardware with ROSC_HW arrow random bit part. The randomness produced by the hardware may have some bias, so using that directly would result in a bad RNG. So to get good RNG, well, we are using a technique called von Neumann whitening or von Neumann debiasing, where we turn 1 zeros into a 1, 0 1s into a 0, and discard the 0 zeros and 1 1s instead of using the zeros and 1s directly from the output. So by this method, you will get like the zeros and 1s almost at the same probability. So that's it with the cryptography. So let's go on to the cryptography on the networking part. So what do we mean by networking here? The goal is to first connect to Wi-Fi with 802.11, which is layer 2, then get an IP address, which is layer 3. Then speak to servers with TCP, that's layer 4. Maybe encrypted with TLS, that's layer 5. Then use HTTP as an application layer, that's layer 6 and 7. So we were missing, what were we missing? We had a hardware driver that's included in the Pico SDK, and TCP IP stack, which is the LWIP, and TLS library, which is an embed TLS, that's also included in the Pico SDK, but we didn't have HTTP. And for the interfaces to Ruby, we had nothing except for the hardware driver, because we had a hardware driver interface that provides Bluetooth. And the hardware driver speaks with LWIP to provide IP setup. Then LWIP speaks with embed TLS to provide TLS over TCP. So what I had to do is mostly came down to writing interfaces to PicoRuby, then implementing basic HTTP with Ruby. So first, we add libraries into R2P2, the CYW43 Arch LWIP thread safe background, the LWIP embed TLS, then also the embed TLS library. And the CYW43 driver, the Wi-Fi driver, and LWIP requires periodic servicing to extract data out of the hardware into the memory. So, and these are handled in two different modes. The first is the Arch LWIP poll mode, which the main program has to poll the Wi-Fi driver periodically to call callbacks and move data out of the hardware. So that is very tedious. So I decided to go with the Arch LWIP thread safe background mode, which runs a background process that handles everything of that. And the handling of the Wi-Fi driver and TCP/IP stack is done in the background, and it's multi-core, multi-thread, multitask safe. There's also an option to use in real-time OS, the free RTOS, but it is overkill to just use it for Wi-Fi, so we didn't go with that. This is what the interface to the driver looks like. That's shown. We've shown that in the video, so please check this later on the slides. And this is how it looks like in Ruby. And after handling the Wi-Fi driver part, I went to make a wrapper for the DNS, and it was actually making easier than making the TCP client. And it is handled by the LWIP library, and it uses UDP to connect to the DNS servers. And how it does that is the DNS get host by name function takes a callback function when the DNS record is found, and most of the rest of LWIPs function like this too. So let's look at an example. The get IP info part has the DNS get host by name, which has a DNS pointer to the DNS found callback function. And if when the DNS record is found, the IP address will be stored in the void arg, and we will copy that value that's stored in void arg into the IP pointer. Then the IP pointer will be returned to the main function. So you've seen that the first call of the HTTPS failed when I showed the demo. So I decided to do some debugging. How I did it is I set up a hotspot with Raspberry Pi, and there's an official tutorial you can follow along, and looked inside packets with Wireshark. This is the packet capture I got. In the top, the capture from the demo shows that it's somehow trying to connect to the IP address 3000, which I don't know where it came from, before the DNS response is received. So it was failing because the IP address T was not properly initialized or zeroed out. So after properly zeroing out the IP address T, you can see that the TCP connection is sent to the correct IP address after obtaining the DNS record. So to implement the TCP client, basically we do the following. We first create a protocol control block, or the PCB, then set callbacks to the PCB for events like when data is received, when data is sent, when an error happens, and when the connection is idle. The library will call the poll function to handle idle connections, like to finish the function when the connection is done. So this is what it looks like. First, we will create the PCB with the ALTCP new, and in the TCP connection state, we hold the pointer to two buffers, the MRBC value send data, which is the data we're sending, and the data we will receive will be stored in the receive data MRBC value, and we're also taking the pointer to the VM to call the MRBC free function to free buffers. And this is what the receive callback looks like. We are getting the packets inside a struct called the pbuff, or the packet buffer, and we will extract the contents of those packets into the receive buffer, which is done in the while loop in the middle. And the part after the while loop is copying into this MRUBC string. And this is the main function for sending data over TCP. So when the connection is complete or encounters an error, the TCP client poll impl function inside the while loop will return a 0. So at that point, the received data value, receive data MRBC value would be ready from the connection, so we can return that value we can return the received data with the ret values. And after getting a TCP client, basic HTTP is very easy. You write HTTP like this in Ruby. So this is a very basic example of a basic HTTP GET. We have something that's more than this. And how to do TLS? With LWIP and application layer TCP, the ALTCP, getting TLS is pretty trivial. Instead of calling ALTCP new to create the PCB, we will be calling the ALTCP TLS new with the client config, then set the host name with the embed TLS SSL set host name. Then the rest is the same. What is going on is that if the PCB is a TLS PCB, when you send data, LWIP will call functions for TLS. Then they will encrypt the data that is written by the TCP sending functions. Then when we receive data, TLS callbacks will be called first to decrypt data. Then the TCP callbacks will be called with the plaintext value. So the cryptography is handled transparently. As such, cryptography implemented in part 1 is not used here, but we can use that in application level cryptographic operations. I said that the TLS was trivial, but it was actually not that trivial because of memory management. LWIP has a separate memory management mechanism from the MRBC VM or the PicoRuby runtime. So when I started implementing TLS, it suddenly hung up with an OOM. So the LWIP used too much memory that it was running into MRBC VM's memory. And I had to reduce PicoRuby's heap memory size from 194 kilobytes to 96 kilobytes, which is about half. It was already small from the beginning, but it's now even smaller. And also, your ordinary mallocs and frees that you use in C does not exist in this environment. They are either MRBC alloc or MRBC free that takes a MRBC virtual machine, or the LWIP's variant that operates differently. I randomly used a free function inside the TCP client code and lost 3 hours from an erratic behavior. And note that this is not the full story. I skipped over many things for time's sake, such as the hardware drivers, periodic servicing part, TCP handshake, TLS handshake, and sending and receiving large chunks of data. The short story is you don't do it because PicoRuby is small. And let's talk about the possible future work. In desktop Ruby, we use TCP socket or socket.tcp, which implements BSD socket-esque API, which is standardized and widely used around many platforms. And LWIP has something like that, but it requires the use of an RTOS. We said that it's overkill for that reason. And MicroPython has a socket-esque API. And I was first going to port MicroPython's network module into PicoRuby, but it was too much work, so I decided to do the basic minimal part first. Then the obvious next step will be servers. This is actually in the works right now with the current API, but I need to come up with an Ruby API API design that will allow Ruby code to handle responses. And this will be significantly easier to do with the socket-esque API. So, but it will be in very limited capability because PicoRuby has also very limited capability. And we were implementing blocking I/O, so what about non-blocking I/O? But is PicoRuby even capable of multiprocessing or multithreading? I am not sure. Raspberry Pi Pico is multi-core, but some hardware that we are targeting aren't even multi-core, so why bother that? So let's conclude our talk. We can hash PicoRuby, TLS and PicoRuby. And yes, these are the stuff that I delivered. We have in PicoRuby RTP2, there's a base 16, base 64, SHA-256, AES, and random number generators. And also, these are experimental, but I'm doing some work to merge it into master. And what's left before merging? I want to rename C functions consistently because we don't have namespaces, and error handling is iffy right now, so I want to fix that. And also, we want to toggle networking with the build flag because if we don't use networking and our RAM is reduced half, we don't want that, right? We want a bigger memory if we don't use networking, so we want to toggle that out. But do we really need TLS? Symmetric cryptography is okay in limited environments, but asymmetric crypto, which is like RSA, elliptic curves, they are very slow. Performance numbers from similar environments show that it takes 6.4 seconds to verify RSA 2048 signatures on a similar hardware. That is too slow, or connections will time out. Also, without a trusted certificate store, we will get encryption through TLS, but not the authentication part of the TLS. For these reasons, depending on your security needs, it would be enough to just use symmetric crypto between the gateway and the Pico, then use TLS from the gateway. Also note that your Wi-Fi password is in your Pico to connect to the Wi-Fi. So if your device gets physically compromised, your Wi-Fi password will be gone. But do you even care about that in most cases? Also, you might want to use a Raspberry Pi 02W, which is a different hardware if you want a more traditional computer experience. It runs a Linux, you can SSH into it, you can run a GUI. Heck, you don't even have to run mRuby. You can just run like CRuby on it. So why do you have to use a Pico? It's closer to hardware, and it's easy to embed into other hardware. So in an IoT environment, these devices work in concert. So with Pico Ruby's Wi-Fi connectivity, we can see actual IoT of Ruby is closer to a reality. And there are some stuff that we can do in the IoT area, like Seaboard COSE co-op support, which is like JSON in binary. And there are like working groups in the IETF that works towards constrained environments, which is equivalent of IoT devices. So we can say Pico Ruby and IoT, that's a blue ocean. The community is waiting for your contribution. And I'm gonna get some shoutouts. Major shoutouts to Hasumi-san for the extensive work in Pico Ruby and help me develop stuff on it. And past RubyKaigi speakers who inspired me to speak here, especially the team protocol implementers, Unasuke-san and Shioi-san. And also to the organizers of RubyKaigi 2024. Thank you for having me here. And also more shoutouts to the sponsors of RubyKaigi that I have personal connections with. They're cool. Go take a look at them. And that's it with my talk. If you have questions, please tweet at me, or if you don't like Twitter, I'm also on Fediverse, so you can post at me there too. Thank you very much.